Today we are going to discuss about fundamental theorem of arithmetic. Fundamental theorem of arithmetic states that every integer greater than 1 is either a prime number or can be expressed in the form of primes. In other words, all the natural numbers can be expressed in the form of the product of its prime factors. To recall, prime factors are the numbers which are divisible by 1 and itself only. For example, the number 35 can be written in the form of its prime factors as 35 is equals to 7 into 5. Here 7 and 5 are the prime factors of 35. Similarly, another natural number 1,14,560 can be represented as the product of its prime factors by using prime factorization method. 1,14,560 is equals to 2 to the power 7 into 5 into 179. So we have factorized 1,14,560 as the product of the powers of its primes. Proof of fundamental theorem of arithmetic. In number theory, a composite number is expressed in the form of the product of primes, and this factorization is unique apart from the order in which the prime factor occurs. From this theorem, we can also see that not only a composite number can be factorized as the product of their prime, but also for their composite number, the factorization is unique, not taking into consideration order of occurrence of the prime factors. In simple words, there exists only a single way to represent a natural number by the product of prime factors. This fact can also be stated as the prime factorization of any natural number is said to be unique except the order of their factors. In general, a composite number A can be expressed as A is equals to P1 into P2 into P3 etc. Pn, where P1, P2, P3 etc. Pn are the prime factors of a written in ascending order, that is P1 is less than or equal to P2 is less than or equal to P3 etc. less than or equal to Pn. Writing the primes in ascending order makes the factorization unique in nature. Prime factorization is a process of factoring a number in terms of prime numbers, that is, the factors will be prime numbers. These prime numbers, when multiplied with any natural number, produce composite numbers. For example, prime factorization of 12 is 2 into 2 into 3, that is equals to 2 square into 3. And again 18 is equal to 2 into 3 into 3, that is 2 into 3 square. 24 is 2 into 2 into 2 into 3, that is 2 cube into 3. 20 is 2 into 2 into 5, that is 2 square into 5. Now let us discuss about factor tree. In factor tree, the factors of numbers are found and then those numbers are further factorized until we reach the closure. Suppose we have to find the factors of 60 and 282 using factor tree. Then see the diagram given below to understand the concept. 60 is divided into 6 into 10. Again 6 is divided into 2 into 3. 10 is divided into 2 into 5. Therefore 60 is equal to 6 into 10. That is equals to 6 into 2 into 3 into 2 into 5. 282. 2 into 141. 347. That is 282 is equals to 2 into 3 into 47. Now prime factors of 27,300. You see, I'm representing composite number with rectangle, prime number with circle. See, it is factorizing 10 to 730. Again, 10 is also a composite and 273 is also composite. Again, this 2730 can be factorized again 10 into 273. Again, 273 is divisible by 3, 391 sa. Again, 91 is a composite number, 317 sa. Then, encircle 17 and 3 because they are primes. Again, go for 10, 2, 5 sa. This is the closure. Therefore, encircle 2 and 5. Again, one more composite number is still there, 10. Again, 2, 5 sa. Yes, this, every number is factorized into primes. Now, prime factors of 27,300 are 2 into 5 into 2 into 5 into 3 into 7 into 13. That is 2 square into 3 into 5 square into 7 into 13. Now I am taking in another way also. 27,300. Previously I started with 10, but now I am starting with 5. 5,460 is. Yes, 5 is prime. I am encircling it. 5,460 is composite. Again, further factorizing as 5 into 1,092. 5 encircle 5. Again, 1,092 is a composite. Factorize it with 2, 546. To encircle it because it is a prime. Again, 546, 2. 2 into 273. Encircle 2 because it is prime. Again, 273 is a composite because it is divisible by 3. 3, 91. Again, 3, encircle 3 since it is a prime. Again, 91 is a composite. 317. Yes, now you see the factors. The order is changed. Now, prime factors of 27,300 are 5 into 5 into 2 into 2 into 3 into 7 into 13. That is again in ascending order, 2 square into 3 into 5 square into 7 into 13. Now I am taking in another way also. 27,300. Now I am starting with 2. 13,650. Again, 13,650 is a composite. 2 further it is divisible. 6,825. Again, 6,825 is a composite. Again, further it is divisible by 5. 1365. Again, 1365 is further divided into 5. 273. Again, this is divisible by 3 only. 391. Again, 3 is prime and circle it. Again, 91. 317. 317. Yes, it is the closure. Now you observe the prime numbers. The prime numbers of 27,300 are 2 into 2 into 5 into 5 into 3 into 7 into 13. That is 2 square into 3 into 5 square into 7 into 13. See, it is unique. In all the 3 cases, just observe on the screen, in all the 3 cases, order may be changed, but finally, if we arrange them in an ascending order, it is unique. Everywhere it is 2 square, 3, 5 square into 7 into 13 in all the cases. Hence, the prime factorization is unique. My dear children, did you understand? See, all the 3 ways which we did there, you observe carefully. Find the prime factors of 1242. Now it is one more other process. Step 1, divide by 2, 620. Divide by 2, 310. Divide by 2, 155. Again in step 4, divide by 5, it is 31. Again 31 divided by 31 is 1. In this way also we can find the prime factors, or in shortcut method 2. 620 to 310 to 155. Again this 5, 31 31 ones. Hence the prime factors of 1240 are 2 cube into 5 into 31. Again let us see one more example of 544 also. Find the prime factors of 544. Step 1, divide by 2, the result is 272. Again step 2, divide by 2, the result is 132. Further it is divisible by 2, it is 68. And step 4, divisible by 2, it is 34. Again it can be divided by 2, it is 17. Again further it cannot. 17 divided by 17 is 1. The same we can express in this way also. 2, 272, again 2, 136, again 2, 68, again 2, 34, again 2, 17. It is further not divisible and 17 ones are 17. Therefore, prime factors of 544 are, here there it is misprint. 544 is 2 to the power 5 into 17. 2 to the power 5 into 17. Express each number as the product of its prime factors. See my dear children, observe carefully on the screen. It is very easy to you to understand. Now 140. Factors of 140 are 2 into 2 into 5 into 7, that is 2 square into 5 into 7. Again 156. 2 into 2 into 3 into 13, that is 2 square into 3 into 13. Now one more, 3825. It is 3 into 3 into 5 into 5 into 17, that is 3 square into 5 square into 17. One more, 5005. It is also very simple, 5 into 7 into 11 into 13. Because there is no square or cube. Now 7479. 17 into 19 into 23, all primes are there. Now find LCM and HCF of the following integers by applying prime factorization method. Observe carefully how we find LCM and HCF using prime factorization method. See, first find the factors of 12 and 15, 21 separately. First, we write the factorization of each of the given numbers. 12, 2 into 2 into 3, that is 2 square into 3. Next, 15. It is only 3 into 5. Again, next 21, 3 into 7. For LCM, we have to take the factors which are not common first. Again, only one time we have to take common. 2 square into 3 into 5 into 7, that is 420 is the LCM of 12, 15, 21. HCF is the common factor, its HCF. 3, 17, 23, and next number is no common factor among them. 17 ones are 17, 23 ones are 29 into 1, 29. No common factor is found among them. Therefore, LCM is the product of the same numbers and HCF is only 1. The product is 11,339. Yes, HCF is 1. Now, 8. Factors of 8 is 2 cube. Factors of 9 is 3 square. Factors of 25 is 5 square. Here also no common factor. Therefore, LCM is the product of all those three numbers. LCM is 2 cube into 3 square into 5 square is equals to 8, 9. 8 into 9 into 25, that is 180. Then no common factor. Therefore, HCF is 1. One more problem we'll see. 17 into 1. Same. Once again, we are repeating that. Given that HCF of 306, 657 is 9, find LCM of 306, 657. We know that the product of HCF and LCM of the two numbers is equal to the product of the given two numbers. Therefore, HCF of 306 in comma 657 into LCM of 306 comma 657 is equals to 306 into 657. Substitute 9. Yes, again bring transpose that 9 to this. The answer is 22,338. Did you understand, my dear children? Question. Check whether 6 to the power n can end with the 0 of any natural number n. If the number 6 to the power n for any n ends with the digit 0, then it is divisible by 5. That is, did the prime factorization of 6 to the power n contains the prime 5? No, not possible. As only prime in the factorization of 6 to the power n is 2 in and 3. And the uniqueness of the fundamental theorem of arithmetic guarantees that there is no n belongs to n for which 6 to the power n ends digit with 0. Explanation. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Since 7 into 11 into 13 plus 13, in these two terms, 13 is common term you have. Take common 13, 7 into 11 into 1 plus 1, that is 13 into 77 plus 1 is 13 into 78. Yes, it is the product of other than 1 and itself. It is a composite number. Now take 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Here 5 is the common factor. Encircle it and common take common 5 into the remaining term 7, 6, 4, 3, 2 in 1 plus 1. That is equals to 5 into, here you multiply all of them, 1 into 2 into 3 into 4 into 7, say 4 into 6 into 7 is 5, this 5 into 1008 plus 1, that is 5 into 1009. So it is also a composite number. Now question, what is the last digit of 6 power 100? The power of 6 to any index repetition 6. That is 6 powered to any number, the last digit is 6 only. Example, 6 to the power 1 is equal to 6, 6 to the power 2 is 36, 6 to the power 3 is 216. The last digit in all cases in this expansion is 6. Therefore, 6 to the power 100 is also 6. Thank you.